First question is how to draw pressure, volume and temperature entropy diagram for Otto cycle, which is thermodynamic air cycle. Second question, solve one problem on Otto cycle by using formulas. Let us understand how to draw pressure, volume and temperature entropy diagram for Otto cycle. All the petrol engines and oil engine run on this cycle. As we are going to consider Otto cycle as a thermodynamic air cycle, that means air is used as a working substance which is enclosed in this piston cylinder arrangement. Now if we observe this diagram, here is hot body, insulated cap and cold body, which we have to brought in contact at the bottom of the cylinder one by one for the different processes. In Otto cycle, two processes are taking place at constant volume process and two processes are at reversible adiabatic or isentropic processes. Now let us consider the initial condition of air. We will consider m kilogram of air is enclosed in this piston cylinder arrangement which is having pressure P1, volume V1 and temperature T1. Now we will locate this point on the diagram. So here suppose this will be the point 1, then here is the pressure P1, volume V1 and for this temperature here is the temperature T1. Now we will move for the process 1 to 2. So what is the first process? So it is reversible adiabatic or isentropic expansion. So for this process, this insulated cap is brought in contact at the bottom of the cylinder. So no heat is rejected or absorbed during this process. Now we will understand what is this isentropic expansion. Here entropy remains constant because the process is isentropic. Now what is the effect of expansion on this temperature, pressure and volume? We know that whenever the expansion is taking place, pressure is getting decreased, and when the pressure is getting decreased, volume is getting increased and temperature is also getting decreased. So we have to show all these processes during the process 1 to 2. So I will show here is the pressure P1. Now at point 2 we have to show decrease in pressure but increase in volume. So I will show here will be point 2, that is for decrease in pressure and increase in volume. We will show arrow also. So here is the pressure P2 and here is the volume V2. Now for the temperature entropy diagram, entropy remains constant and temperature is getting decreased. So we will show here straight vertical line. Here will be the point 2. So here is temperature T2 and here S1 is equal to S2, that is entropy will remain constant. So all the conditions are getting satisfied. Now we will move for the next process. Next process is constant volume cooling. Now if we observe this diagram, here this cold body is brought in contact with the bottom of the cylinder and that's why the cooling process is taking place. So how to show this cooling process? Condition is that volume remains constant. So here we have to show constant volume, that is straight vertical line. Then what is happening when the cooling process is taking place? So when cooling process is taking place, that means temperature is getting decreased. So when the temperature is getting decreased, it's a pressure we have to show also getting decreased. And when the cooling process is taking place, that means entropy is getting decreased. So we have to show decrease in entropy, decrease in temperature and decrease in pressure. And we have to show the constant volume. So I will show here. So decrease in pressure and volume will remain constant. So here will be point 3, that is P3 and V2 is equal to V3. Then we have to show here decrease in entropy and decrease in temperature. So we have to show, I will show here with straight inclined line, that is this will be the point 3, here will be temperature T3 and entropy S3. Now this is the cooling process. So what is happening in cooling process? That is the heat is getting rejected. So what is the amount of heat is getting rejected during the process 2 to 3? Now this process is taking place at constant volume. So we have to consider the specific heat at constant volume, that is Cv. So here formula is Q23 is equal to mCv T2 minus T3. So this is the formula that we have to use for the calculation. Now we will move for the next process. So next process, that is process 3 to 4, reversible adiabatic or isentropic compression. Now here this reversible adiabatic, that means, or isentropic, that means entropy remains constant and the compression process is taking place. So for the process 3 to 4 we have to show constant entropy. And here we have to show for the compression process, that means what is the effect of compression on pressure, volume and temperature. So when the compression is taking place, we know that pressure is getting increased, and as pressure is getting increased, temperature will also getting increased. And what is the effect? That is effect on volume, that is during compression process volume is getting decreased. For this process 3 to 4 we have to select the point 4. Now if we observe this pressure volume diagram, we have to take care for one point. That is, when we are going to select the point 4, then P2 should be less than P4. So here is the pressure P2 and this should be less than P4. That means we will select here point 4. That means P4 should be slightly greater than P2. So here will be our point 4 and here this condition should be satisfied. That is P2 should be less than P4. So here the pressure, if we compare this point 3 and point 4, pressure is getting increased and volume is getting decreased. So we will join these 2 points. Now we will move for the temperature entropy diagram. So here also we have to select the point 4. So how to select the point 4? So here we have to show constant entropy, that is straight vertical line, but we have to take one condition, that is T4 should be less than T2. So here T4 should be less than T2, that is here is T2 and we have to take the point 4 slightly below that. So here if I take this T4, then I will select here the point 4 and we will draw here the straight vertical line. So in this way this is getting completed. So in this process no heat is absorbed or rejected, because if we observe this isentropic compression process, again the insulated cap is brought in contact with this bottom of the cylinder. Now we will move for the next process, that is the constant volume heating. So for this process hot body is brought in contact at the bottom of the cylinder and the heating process is taking place. So what is happening when the heating process is taking place? Here condition is that volume should remain constant. So whenever the heating process is taking place, then we have to show increase in pressure. So as pressure is getting increased, temperature is also getting increased. Because of heating, we have to show increase in temperature also, and because of heating, entropy is getting increased. So we have to satisfy all these conditions. So when we join these two lines 4 to 1, we have to draw straight vertical line, because V1 is equal to V4 and there should be increase in pressure. So here and here also we will join this 4 and 1. So if we observe entropy is getting increased, then temperature is also getting increased. That means all the conditions are getting satisfied. Now in this process, heat is getting absorbed by the air. So how to calculate this amount of heat? So Q41 is equal to mCV T1 minus T4. Now why here specific heat at constant volume? Because this process is taking place at constant volume, and we have to take the difference in between temperature, that is T1. T1 is greater than T4, so T1 minus T4. Now we will understand some formulas. So first one is work done. So work done is equal to heat absorbed minus heat rejected. So heat absorbed during the process 1 to 4 and heat is rejected during the process 2 to 3. So here is the formula mCV T1 minus T4 minus mCV T2 minus T3. Then efficiency. So efficiency is neta is equal to work done by heat absorbed. So we have to write all these formula for the work done divided by heat absorbed, that is mCV T1 minus T4. So if we take mCV as a common term from numerator, then from the numerator and denominator mCV is getting cancelled. So what is remaining? That is T1 minus T4 minus in the second bracket T2 minus T3 divided by T1 minus T4. So again this T1 minus T4 is getting cancelled, so which is equal to 1 minus T2 minus T3 divided by T1 minus T4. Now we will move for the next. We know that there are two processes that are taking place at the constant entropy, and these processes are 1 to 2 and 3 to 4. Now we will consider the isentropic index, that is gamma, and we will write some formulas. That is, these formulas is nothing but the relation in between temperature, pressure and volume when the entropy remains constant. So what is that relation? So we will take here the ratio. So first we will take the process 1 to 2, which is isentropic. So when isentropic process is taking place, then the ratio of temperature, that is T2 by T1, is equal to V1 by V2 raised to gamma minus 1, and which is equal to P2 by P1 raised to gamma minus 1 by gamma. Now in the same way during the process 3 to 4, so which is also isentropic process, so here we will take ratio T3 by T4 is equal to, so which is equal to V4 by V3 raised to gamma minus 1, which is equal to P3 by P4 raised to gamma minus 1 by gamma. Now if we observe this diagram, so during the process here 1 to 2 and 3 4, here V2 is equal to V3. So I will put here V2 is equal to V3 and V1 is equal to V4. So I will put here V1 is equal to V4. So I will write here V4 divided by V3 raised to gamma minus 1. So because V2 is equal to V3 and V1 is equal to V4, so which is equal to V4 by V3 raised to gamma minus 4. So if we observe this V4 by V3 raised to gamma minus 1, and here is also V4 by V3 raised to gamma minus 1. So from this we can say that T2 by T1, which is equal to T3 by T4. Now we will solve one problem. I will read what is the given question. Air at a pressure of 1 bar and temperature 70 degrees Celsius is compressed reversibly and adiabatically until the pressure is 7 bar in an Otto cycle engine. 460 kJ of heat per kilogram of air is now added at a constant volume. Determine compression ratio of the engine, temperature at the end of compression and temperature and at the end of heat addition. Take for air Cp 1 kJ per kilogram Kelvin, Cv 0.707 kJ per kilogram Kelvin. Let us understand what is the given data. It is given that at a pressure of 1 bar and temperature 70 degrees Celsius, air is getting compressed up to a pressure of 7 bar. Now we will understand this with the help of this diagram. Now where is the compression process is taking place? So if we observe this diagram, then the compression process is taking place during the process 3 to 4. because we know that here the isentropic compression and isentropic expansion process is taking place. So compression process is 3 to 4 and expansion process is 1 to 2. So here before compression, what will be the temperature and pressure? So before compression, that is at point 3. So pressure we will say here as a P3 is equal to 1 bar, and temperature we will say T3 is equal to 70 degrees Celsius. So we will convert this into Kelvin, that is 70 plus 273, that is 343 Kelvin. Now after compression, pressure reaches to 7 bar. So when the compression process is taking place, then it will move from point 3 to the point 4. So here is the pressure, that is P4 is equal to 7 bar. Now heat addition process is taking place, and what is the amount of heat addition? That is 460 kilojoule. So we know that during the process 1 to 4 there is the heat addition process is taking place at constant volume. So what is the heat involved is Q14. So we have to write Q14 is equal to 460 kilojoule, and this amount is per kilogram, that is mass of air m is equal to 1 kilogram, that we have to take this value. Then Cp, that is the specific heat at constant pressure, is 1 kilojoule per kilogram Kelvin, and Cv, that is specific heat at constant volume, 0.707 kilojoule per kilogram Kelvin is given. Now from these values we can calculate the isentropic index, that is gamma. So gamma is nothing but Cp by Cv. So Cp by Cv, that is 1 divided by 0.707, which is equal to 1.41. So we have to use this value of gamma, 1.41. Now we will move for the calculation part. So what is the calculation? So during the compression process, we will first find out what is the ratio of V3 by V4. Now if we observe, this is the compression ratio, that is V3 divided by V4. So how to find out that? So during the compression process, P3 V3 raised to gamma is equal to P4 V4 raised to gamma. So this is the law that is followed. Now we will simplify this. So we will take V3 by V4, that is I will take here V4 to the left hand side and I will transfer this P3 to the right hand side. Then what will happen? V3 by V4 bracket raised to gamma is equal to P4 by P3. Now we will transfer this gamma also to the right hand side. So this gamma will become 1 by gamma. So V3 by V4 is equal to P4 by P3 raised to 1 by gamma. Now what is the value of P4? That is 7 bar. And what is the value of P3? That is 1 bar. So 7 by 1 raised to 1 divided by 1.41, which is equal to 3.97. So this is the compression ratio, or we can say V3 by value of V3 by V4. Now we will move for the second question, that is we have to find out what is the temperature at the end of compression. That means we have to find out the temperature at point 4, that is T4. Now during isentropic process, so this process is the isentropic process 3 to 4. So during isentropic process we have already seen formulas, that is the relation in between this temperature and volume. So we know that T3 by T4 is equal to V4 by V3 raised to gamma minus 1. So now we know that value of V3 by V4. So here is V4 by V3. So we will take here 1 divided by 3.97 raised to gamma minus 1, that is 1.41 minus 1, that is 0.41. So which is equal to 0.568. Now we have to find out the temperature at point 4, that is T4. So what is the temperature T3? That is 343 Kelvin. So we have to take the value in Kelvin, so that answer we will get in Kelvin only. So T4 is equal to 343 divided by 0.568, which is equal to 604 Kelvin, and which is equal to 331 degree Celsius. Now we will calculate what is the temperature at the end of heat addition. Now if we observe this diagram, heat is getting added during the process 4 to 1. So Q14 is given 460 kilojoule. So how to calculate this? Because this process is taking place at constant volume, we have to take the formula, that is MCV T1 minus T4. Now this T4 is getting calculated. M is equal to 1 kilogram, CV is given and Q14 is also given. So 460 is equal to, we will put all the values, and here if we transfer this 0.707 to the left hand side, then T1 minus 604 is equal to 651 and T1 is equal to 1255 Kelvin, and which is equal to 982 degrees Celsius.